Hello, my name is Bryan Harris from the University of Louisville, presenting ultra-low latency SSD's impact on overall energy efficiency. In this paper, we investigate the energy characterization of an Optane SSD and the impact of ultra-low latency storage on overall system energy efficiency. First, by ultra-low latency, or ULL, we refer to a new generation of storage that is broadly defined as providing around 10 microsecond data access latency. Examples of these devices are Samsung's Z SSD based on 3D NAND technology, Toshiba's XL Flash, and Intel's Optane SSD. Optane SSDs are currently the most promising ULL SSDs and the most widely available and cost-effective. Optane is based on 3D XPoint, which is Intel and Micron's proprietary phase change memory technology. Optane is ideal for applications that require low latency access. The primary motivation for this work is ultimately to save energy, and this requires greater understanding of energy efficiency in technologies such as Optane and, more generally, ultra-low latency storage devices. Existing studies of Optane SSDs primarily focus on performance rather than energy efficiency. Those that do investigate power measure only the individual storage device or CPU utilization rather than the total system. The power consumption characteristics of Optane SSDs and their 3D XPoint technology are largely unknown. In addition, ultra-low latency devices put increased pressure on system software. To our knowledge, no previous work has investigated the impact of this level of performance on overall energy efficiency. We tested 4 storage devices, an HDD, 2 flash-based SSDs, and an Optane SSD. These have roughly similar price points, around $200 or $300 each. They represent 3 generations of technology, magnetic, flash, and 3D XPoint, and 2 interfaces, SATA and NVMe. We empirically measured the power usage of a 1-unit Dell Enterprise system using an inline plug meter. This meter records power measurements in its embedded memory, which is later read out through a USB interface. This removes any overhead of power measurement. We used FIO to generate I/O workloads to push the storage system. In order to capture the maximum range of effects on the system, we wish to push the storage device to its limits. We submit asynchronous direct requests with a wide range of sizes and I/O queue depths. Now our observations. First, we examine idle versus active power consumption. In order to measure idle power, we install only a single test device, allow the system to boot, and sit idle for 10 minutes. Hard disk drives have a notoriously high idle power consumption because the platters spin regardless of activity. This issue was alleviated when solid-state flash storage was introduced. However, we caution that new high-performance devices, such as Optane SSD, may lose this improvement. We believe this may be due to a high-performance controller design, the internal physics of 3D XPoint technology, and the lack of support for autonomous power state transitions, or APST. In order to analyze active power consumption, we run storage workloads across a range of behaviors from low to high intensity and record the overall power consumption of the system. The top of each bar represents the maximum power observed across all workloads for each device. Notice that with newer devices and lower latency, active power increases. The power range of the system from idle to active is, of course, not due solely to the storage device, as there are other system components, such as CPU and RAM, that are also impacted by ultra-low latency I/O. As we will see, having a greater range of power is key to enabling greater energy proportionality. We examine the differences in power consumption of read and write workloads, or what we call read-write energy asymmetry. White is roughly asymmetric, where reads and writes use approximately the same power. Orange is where writes use more power, and purple is where reads use more power. We can clearly see the trend for greater distinction with newer generations. Notice this distinctive change in 1 kilobyte requests at the bottom row of Optane. These are the tiny requests prescribed to avoid in last year's HotStorage paper towards an unwritten contract of Intel Optane SSD. Energy proportionality means consuming energy in proportion to the amount of work performed. The ideal energy proportional machine uses zero power when idle and its maximum power at its peak utilization. Energy proportionality is valuable to data centers due to their high cost of electricity. A characteristic feature of this proportionality is a wide dynamic power range, as it allows for a change in power with respect to utilization. In our study, we normalize system power to the maximum power that we observed for our test system. Storage performance utilization is throughput, or IOPS, normalized to peak throughput for each device. The HDD, or this red line, is clearly not energy proportional. Its power usage is flat, as it consumes approximately the same power regardless of the amount of work it performs. On the other hand, the flash-based SSDs are more energy proportional, as they show an increase in I/O performance with greater power usage. However, the Optane SSD is the most energy proportional, as it shows the greatest range of power usage, spanning more than half the peak system power, which makes it ideal for use in energy-efficient data centers. As many of you would know, ultra-low latency performance puts increased pressure on system software, especially when using interrupt-based I/O mechanisms. This increased pressure results in more overall energy consumption. Here we show how increased storage load, or I/O depth, increases pressure in the form of increased rate of interrupts. As you can see, it gets rather high, around 600,000 interrupts per second. Increased pressure on system software is also indicated by greater kernel CPU utilization. However, we realize that measuring CPU utilization by itself may be misleading when designing energy-efficient systems. Researchers should always consult overall power consumption. These two figures show CPU utilization and power consumption, both as a function of storage interrupts per second for 4 kilobyte random reads and writes. On the left, writes for Optane SSD, this green dashed line, caused around 300% system CPU with an interrupt rate of 400,000 per second. But reads, this solid green line, caused only 100% system CPU with an interrupt rate of 600,000 per second. A similar imbalance exists for the flash NVMe. However, their overall power consumption, on the right, is not directly proportional to their CPU utilization, where peak power consumption for reads is slightly greater than for writes. Zadok has used the energy efficiency metric of operations per joule. Here we use two similar metrics based on performance per unit energy, or performance per joule, one based on bandwidth and the other on throughput. Bytes per joule is bandwidth per unit energy, and IOs per joule is throughput per unit energy. In these figures, green is more efficient, with more bytes transferred per joule. We notice that larger requests are more efficient than smaller requests. Even though more data is transferred, the energy cost of transferring additional data in one request is less significant than the cost of managing the request itself and the pressure put on system software. Being the lowest latency device, Optane finishes a request faster than the other devices. This results in greater efficiency despite being a higher power device. Here we can also see the inefficiency of serving the 1 kilobyte tiny requests. Here we show energy efficiency as measured in IOs per joule. Notice that for Optane, increased IO depth does not correspond with increased energy efficiency beyond a saturation point. We attribute this to the limited parallelism of the Optane SSD. The flash NVMe, on the other hand, has much richer internal parallelism and increased power consumption, therefore corresponds to continuously increasing IO performance. These last two observations outline best practices for overall energy efficiency. Optane SSD has the greatest energy proportionality since its power consumption scales better than previous storage generations based on its range of throughput. Although Optane's peak power consumption is higher, it yields better energy efficiency as measured in both bytes per joule and IOs per joule. Our topics for discussion and areas of future research are to rethink system software for energy efficiency. Given the negative impact of low latency block devices on operating systems, are there ways to reduce or simplify system software in order to save energy? What about polling or hybrid polling versus interrupts? New I/O interfaces such as IOU ring, the kernel bypass SPDK, and so forth. Are there simpler mechanisms for block multi-queue and NVMe interface that would save energy? What about different I/O scheduling algorithms? Merging, prefetching, buffering, or log structuring. What effect does this have on energy efficiency? We would also like to investigate this read-write asymmetry that we observed. Why do writes use more CPU but fewer interrupts? Do existing design choices get in the way of 3D crosspoint, both in terms of performance and energy? Are there strategies for hybrid drives for energy efficiency that would merge, say, 3D crosspoint and flash? We are also interested in energy efficiency as a whole. Do optimizations for storage performance lose sight of energy efficiency? Compared to other system hardware like CPU and memory, storage devices often use less power. Is the energy impact of the storage subsystem underestimated or neglected? Thank you for your attention. I would also like to thank the HotStorage organizers and committee, our anonymous reviewers, and our shepherd for the opportunity to share our work with you. If you have any questions, please contact us with these addresses below. Thank you.